You feel still right now, but that feeling is lying to you. You live on a sphere about 12,742 kilometers across, roughly 7,900 miles, and it is rotating under you at around 1,670 kilometers per hour at the equator, about 1,040 miles per hour. That is faster than a typical passenger jet, all the time, every day of your life. You do not hear it, you do not feel pressed back in your seat, yet your position in space is changing by hundreds of meters every second, just because Earth is turning. But before we continue, please subscribe to the channel to give your support. Let's continue. Zoom out one step from your house, your street, your city. All of that is painted on a thin outer layer of this planet, a layer only a few tens of kilometers thick compared to the full diameter of over 12,000 kilometers. Almost everything you care about, every building, every road, every person, fits inside that tiny surface shell. Under that thin layer, most of the planet is rock and metal under high pressure and high temperature, and the whole structure is spinning as one object. On top of that rotation, Earth is also moving around the Sun at about 30 kilometers per second, around 67,000 miles per hour. So when you think you are staying in one place, you are actually drawing a long curved path through space, tied to a rotating, orbiting planet that never slows down. If being still already means moving at jet speed around a huge rock, how large is the next layer of your environment, the one that includes the moon? The moon feels close because you see it with your naked eyes. It hangs comfortably over your horizon, but the distance is already extreme. The average gap between Earth and the moon is about 384,000 kilometers, roughly 239,000 miles. That number is easy to say and hard to feel, so break it down in a very simple way. Take a car, lock it at 100 kilometers per hour, about 60 miles per hour, and aim straight up. No traffic, no stops, no fuel problem. At that constant speed, you would need more than 4 months of non-stop driving to reach the moon. 4 months just to leave the immediate neighborhood of your planet and arrive at the closest large object in space. And that Earth-Moon system is still tiny compared to the structure that controls both of them, the Sun. Even after driving for months in that thought experiment, you would still be inside a very small bubble of the solar system. The moon's orbit is wide compared to Earth, but it is extremely close compared to the scale of the sun's reach. So if 4 months of continuous travel only gets you to the moon, what does the next step up look like? The step where the sun becomes the main reference point. The sun sits about 150 million kilometers away from you, roughly 93 million miles. That is the average Earth-Sun distance, and in astronomy, it is so large that it gets its own name, one astronomical unit. To send light across that gap, even at 300,000 kilometers per second, 186,000 miles per second, takes about 8 minutes. In 1 second, a beam of light could go around Earth more than 7 times, but it still needs minutes to bridge the space between you and your star. This means you never see the sun as it is right now. You always see it as it was roughly 8 minutes ago, because the information about its surface, carried by photons, is still in flight when you look. Compared to your usual daily distances, a few kilometers, a few dozen kilometers, this 150 million kilometer baseline is completely different. Yet people treat it as ordinary background, as if it is just another big number in a textbook. And that is just the inner scale. The solar system extends much farther than the orbit of Earth or even the orbit of Neptune. So the next logical question is simple and uncomfortable. Where is the real edge of the system you live in? For a long time, school diagrams made Pluto feel like the outer boundary. Pluto orbits at about 5.9 billion kilometers from the Sun, around 3.7 billion miles. That is already almost 40 times farther out than Earth. At that range, sunlight is dim and weak, and orbital periods stretch to over 200 Earth years. It feels natural to say, okay, that's the end. But it isn't. Beyond the planets, there's a huge region filled with icy bodies, mostly invisible from here, called the Oort cloud. We infer its existence from the way long-period comets fall towards the inner solar system from all directions. The distances involved are completely different from planetary orbits. The Oort cloud probably extends out to about 100,000 astronomical units. One astronomical unit is that 150 million kilometers you heard earlier. Multiply that by 100,000, and you get a radius of roughly 1.5 light years. On that scale, the numbers in kilometers or miles become almost useless in day-to-day thinking. That outer region is so far away that it's comparable to the thickness of the Milky Way's disk. Just a cloud of leftover icy debris loosely held by the sun's gravity already reaches a scale where you can start comparing it to parts of your entire galaxy. And despite that, your brain still files the solar system as something small and close, something you feel you live inside, almost like a big version of a city. So you have this situation. Your practical life is locked to a tiny surface layer of a spinning planet. That planet orbits a star 150 million kilometers away. That star controls an extended system of planets and distant icy objects stretching over a light year in radius. And all of that is still a microstructure from a larger point of view. Your whole solar system, including the Oort cloud, is just one dot among many in the Milky Way. From the perspective of the galaxy, your entire cosmic address so far is smaller than a single pixel. All human history, every satellite, every probe you have ever launched fits inside that pixel. And that pixel sits in one modest spiral arm of the Milky Way, which itself is not the only large galaxy in your region of space. There's another major one, Andromeda, about 2.5 million light-years away, with its own hundreds of billions of stars, its own planets, its own unknown worlds, and that is not just sitting there quietly. Gravitationally, the Milky Way and Andromeda are locked together. They pull on each other across those millions of light years. The orbits of stars, the shapes of their dark matter halos, the future paths of both galaxies are all being slowly adjusted by this interaction while you live your life without noticing any of it directly. You are inside a tiny moving system, inside a bigger moving system, inside an even larger pair of interacting systems, and at every step, your usual sense of distance collapses. So here's the next step in the tension. Kilometers and even billions of kilometers are starting to fail as useful units. The numbers are too big, and the scales are too wide. To really handle the size of the gap between you, your galaxy, and Andromeda, you need a different ruler, one built out of light itself. And once you switch to that ruler, even the fastest thing in the universe starts to look slow. You've been using the wrong ruler for the universe your entire life. Kilometers and miles work for roads and flights, but they completely break when you try to measure the space between stars and galaxies. That's why astronomy quietly switches to something else, a unit so extreme that your brain wants to think it's about time, not distance. A light year. It sounds like a countdown. It's actually a length. A light year is how far light travels in 1 year. Light moves at about 300,000 kilometers per second, around 186,000 miles per second. Stack those seconds for a full year, and you get a distance of about 9.46 trillion kilometers, nearly 6 trillion miles. That's 1 light year. Not a time span, not a sci-fi phrase, just a brutal distance unit that makes your normal idea of far look tiny. To see how ridiculous that is, pretend you push something much slower but familiar to the limit. Take a racehorse and lock it at 60 kilometers per hour, about 37 miles per hour, forever. No rest, no food issues, no injuries. At that constant pace, it would need on the order of 18 million years to cover 1 light year. That's tens of millions of years of full speed running just to tick off a single unit on the cosmic ruler. This is why no one talks about driving or flying a light year. Human muscles, engines, all of it is meaningless at the scale. So here's the next question that ramps things up. If 1 light year is already completely out of reach for anything you can build today, what does your actual stellar neighborhood look like when you measure it with this ruler? Your closest star system, Alpha Centauri, is not a quick trip. It sits about 4.37 light years away. Turn that back into the old units and you get roughly 41 trillion kilometers, a bit over 25 trillion miles. On paper, that's just another big number, but line it up against what our best machines can actually do and the picture gets harsh. Right now, the fastest spacecraft humans have ever launched are moving at tens of kilometers per second relative to the sun, tens of thousands of kilometers per hour, tens of thousands of miles per hour. That sounds fast in everyday terms. At those speeds, you can cross a planet in hours. But stretch that to 4.37 light years and the travel time explodes into tens of thousands of years. Not long road trip, not multi-generation mission, but more like older than any known human civilization just to reach the nearest star system. And that's if you point the spacecraft perfectly and nothing breaks. So just to knock on the door of your closest stellar neighbor, you are already outside the range of anything your species has ever maintained. And that's just the first step out from the sun. So here's the escalation. If your next door star is that unreachable, what does the distance to a whole other galaxy look like in the same units? Andromeda is not measured in a few light years. Its distance is about 2.5 million light years. Take that 9.46 trillion kilometer light year and now multiply by 2.5 million. You end up with a distance of roughly 2.4 times 10 to the power of 19 kilometers, which is about 1.5 times 10 to the power of 19 miles. Those numbers are so big that they stop feeling like distances and start feeling like some kind of error message. But they are real. Here's a more grounded way to sense it. The average Earth-Sun distance, 1 astronomical unit, is about 150 million kilometers, 93 million miles. Now picture the Milky Way as your house sitting at that scale. Andromeda would be another house not just a few houses down the street, but about 25 million Earth-Sun distances away. Not 25 million kilometers, 25 million times 150 million kilometers. The gap between the two big galaxies in your local group absolutely dwarfs any distance you have words for in everyday life. And yet, as crazy as that separation is, nature still lets light cross it. Photons leave Andromeda, travel for millions of years, and eventually some of them hit your telescope mirror or even your retina. That leads directly into the next uncomfortable question. If light has to work that hard to get here, what exactly are you looking at when you see that galaxy? Every time you look at Andromeda through a telescope, you're looking 2.5 million years into the past. That fuzzy glow in the sky is not Andromeda right now, it's Andromeda as it was when that light started its journey. On Earth, 2.5 million years ago is way before Homo sapiens. Our own species is probably only a few 100,000 years old. So you, as a modern human, are younger than the image you see. The light you're catching left long before humans like you existed, crossed intergalactic space while your ancestors were somewhere on the path from early hominins to what you are now, and is only arriving today. This isn't a trick, it's just how finite speed works on huge distances. The farther away something is, the older version of it you see. Look at the moon, you see it about a second and a bit in the past. Look at the sun, about 8 minutes in the past. Look at Andromeda, 2.5 million years in the past. Your eyes, plus a telescope, are literally time machines, but they can only look backward, never forward. That raises the most disturbing part of this whole section. If even light is this slow on cosmic scales, what does that mean for your picture of what really exists right now out there? The speed of light, roughly 300,000 kilometers per second, 186,000 miles per second, is not just a fast thing. It's the ultimate speed limit of the universe as far as we know. Nothing with mass gets to outrun it. But on the scale of galaxies, that ultimate speed starts to look painfully slow. Andromeda itself is huge, likely over 150,000 light-years in diameter, possibly up to around 260,000 light-years, depending on how you define the edge. A beam of light fired from one side of Andromeda to the other would need hundreds of thousands of years to cross the disk. So there is no such thing as one single present moment for a whole galaxy in any practical sense. Different parts of Andromeda are seeing different versions of each other, offset by hundreds of thousands of years. You never see Andromeda as it really is in one instant. You only see a stitched-together delayed snapshot. Outer parts as they were earlier, inner parts as they were slightly later, all of it also delayed again by 2.5 million years on the way to you. So here's the pressure point this section leaves you with. Your main unit for measuring cosmic distance is built from the fastest thing in existence, and even that is too slow to keep one galaxy in sync with itself. If light needs hundreds of thousands of years just to cross a single galaxy, and millions of years to cross the void between the Milky Way and Andromeda, what does that say about how utterly small your solar system is compared to even one galactic disk, and how tiny that disk is compared to the full structure of the Milky Way you are actually orbiting inside? If your fastest unit, the light year, already makes your head spin, what happens when you ask a harder question? How big is the thing you're actually orbiting inside right now, the Milky Way itself? Your solar system feels large when you think about billions of kilometers, but compared to the galaxy, it is microscopic. The main disk of the Milky Way, the region where most of the stars live, is roughly 87,000 to 100,000 light years across. Draw a straight line from one edge of the starry disk to the other, and you are talking about a distance where light, moving at 300,000 kilometers per second, needs up to 100,000 years to cross from side to side. In thickness, that same disk is only about 1,000 light years tall in the spiral arms. So the whole thing is a huge flat sheet of stars, wide in the plane, thin in the vertical direction. Your sun, your planets, the Oort cloud, all sit inside that thin layer, not above it, not below it. You live buried in the disk. From inside, you never see the Milky Way's true shape directly. On a dark night, away from city lights, you see a bright band across the sky. That band is you looking along the plane of the disk, through thousands of light years of stars and dust. But you are stuck in the middle of the structure. It's like trying to understand the shape of a forest while standing between the trees. You see trunks and branches in every direction, but the big pattern is hidden. So here's the next hit to your ego. If the galaxy is that wide and that thin, where exactly is your solar system in that giant structure, and how is it moving? Your sun is not parked in space, it is in orbit. It circles the center of the Milky Way at a speed of about 220 kilometers per second, around 490,000 miles per hour. That is far beyond the speeds you deal with on Earth. At that pace, you could go from Earth to the moon in under an hour if you could somehow fly in a straight line. But instead, the sun is using that speed to trace a huge, almost circular path around the galactic center. One full lap, one galactic year, takes roughly 225 to 250 million Earth years. From the time of the early dinosaurs until now, the sun has done about one full orbit. All of recorded human history, everything from the earliest writing to your phone right now, fits into less than 2,000ths of a single galactic year. That is about 0.2% of one orbit. Humans as a species have existed for a tiny fraction of one lap around the galaxy, and your entire technological civilization is a thin slice on top of that. Now it gets more uncomfortable, because even though you are inside this huge, fast-moving system, how much of it have you actually seen in detail? Even with the largest telescopes on the ground and in space, the fraction of the Milky Way we have mapped at high resolution is small. Thick clouds of dust and gas block our view along the plane of the disk in visible light. When you look toward the center of the galaxy with normal cameras, you see a lot of stars, but you also see dark patches where dustlings sit in front and absorb the light. To cut through that, astronomers use radio waves and infrared light, which can pass through dust much better. With those tools, they can trace spiral arms, see star-forming regions, and map gas clouds. But your mental picture of a spiral galaxy is mostly stitched together from images of other galaxies, ones we can see from the outside. The classic photos you know, the big pinwheel shapes, are almost never the Milky Way. They are other galaxies at the right distance and angle that let us guess what ours looks like. So even your idea of your own galaxy structure is in a sense secondhand information, a reconstruction, not a direct selfie. So that raises a simple question. Inside that huge, partly hidden disk, where is the sun actually sitting, and is it anywhere special? Your solar system is not near the center. It is about 27,000 light-years away from the galactic core, roughly halfway between the center and the outer edge of the disk. And it is not in one of the big, bright main spiral arms either. It sits in a smaller structure, often called the Orion arm or the Orion spur, basically a side branch between two larger arms. In terms of galactic real estate, this is not the downtown core. It's more like a quiet side district away from the crowded central bulge and the dense star-forming regions. That location has consequences. Being away from the most crowded, violent zones may actually make long-term stability easier for planetary systems like yours. Fewer nearby supernova blasts, fewer close gravitational encounters with other stars, a bit less chaos. But it also means when you look up, you are seeing the galaxy from one very local, specific vantage point, not from some central control room. You are not at the center of anything large-scale here. You are on the outskirts of a medium-sized spiral, in a minor arm. And that sets up the next twist, because even though the Milky Way already dwarfs everything in your direct experience, it's not the heavyweight champion in your own neighborhood. Andromeda, your big neighbor, is larger in diameter than the Milky Way in most measurements, and is probably more massive overall once you include its dark matter halo. Where your galaxy's disk is around 100,000 light-years across, Andromeda's can reach well over 150,000 light-years, maybe more, depending on where you draw the line. And it's not just sitting still, it's moving toward you at about 110 kilometers per second, roughly 68 miles per hour. On human scales, that is an extreme closing speed. On galactic scales, it's a slow, steady approach that will reshape both galaxies over billions of years. So line this up clearly. You live on a tiny planet around one star, inside a thin disk about 100,000 light-years wide, orbiting a center you will never visit, in a galaxy that's not even the largest in its own small group, with a bigger system, Andromeda, already on a collision course. If this is what home looks like on the galactic scale, what happens when you zoom in on that approaching giant and see how much it outclasses the Milky Way star for star? You've heard that Andromeda is a big galaxy, but that phrase is hiding the real scale jump here. Your own galaxy, the Milky Way, has a stellar disk maybe 90,000 to 100,000 light-years across. Andromeda's disk is more like 150,000 to over 260,000 light-years across, depending on where you decide the faint outer edge stops. So you go from an already huge system where light needs about 100,000 years to go side to side, to one where light can need more than twice that. You're dealing with a structure where the basic diameter is hundreds of thousands of light years. The star count makes the gap even worse. The Milky Way probably has a few 100 million stars, already a ridiculous number. Andromeda may host something closer to 1 trillion stars. That's a factor of 3 to 5 more. So if you picture every star in the Milky Way getting its own slot, Andromeda has enough stars to fill all those slots and still have hundreds of billions left over. In raw stellar inventory, your galaxy is not the boss here. It's the smaller partner in a 2-galaxy system. So here's the weird part. If Andromeda is that large and that full of stars, why does it look like such a small, harmless blur in your sky? On the sky, Andromeda stretches around 3 degrees from end to end. The full moon is about half a degree across. That means the apparent size of Andromeda is roughly 6 times the width of the moon. In angle, it's big. But when you look up, you only notice a small bright core and maybe a faint smudge around it, not a giant stripe of galaxy dominating everything. The reason is not that Andromeda is small, it's that your eyes are bad at low-light imaging. Your night vision has terrible resolution and sensitivity compared to a camera with a long exposure. The outer parts of Andromeda's disk are extremely faint, spread over a large area of the sky. The surface brightness is too low to trigger a detailed picture on your retina. Your visual system compresses that extended glow into a vague patch, and your brain silently underestimates how big it really is. So you get this paradox. One of the largest objects in your neighborhood is sitting there, spanning multiple moon widths in your sky, and most people never notice it at all. That leads to a very direct question. What does it say about your senses that you can see a different galaxy with no telescope at all and still not treat it as something huge? Under a dark, rural sky, away from city lights, you can see Andromeda with the naked eye as a small, fuzzy spot. No binoculars, no observatory, just your eyes. That blur is the combined light of billions of stars, 2.5 million light-years away. In distance, that's about 2.4 times 10 to the power of 19 kilometers, roughly 1.5 times 10 to the power of 19 miles. Your normal distance sense is built for kilometers and maybe thousands of kilometers. Here, with no effort, your retina is catching photons that have flown across intergalactic space for millions of years. You're used to the idea that you can see a city from far away if the air is clear, but this is a different level. You're seeing something so far that any vehicle you can currently build would need tens of billions of years or more to cross that gap at its current speeds. The fact that this shows up as a casual blur you can point to with your finger is not a sign that it's close. It's a sign that light is extremely good at traveling, and your brain is extremely bad at judging space at these scales. So if your eyes drastically downplay Andromeda's size, what is actually going on inside that blur? Is it just a static ball of stars or something more dynamic? Andromeda is a rotating disk galaxy, not a motionless cloud. Its stars orbit the galactic center at speeds of hundreds of kilometers per second, similar to the orbital speeds in the Milky Way's disk. Gas and dust follow complex paths, spiral arms wrap around the core, and regions of intense star formation light up in ultraviolet and visible wavelengths. When you see a textbook picture of a spiral galaxy with clear arms, dust lanes, and bright knots where new stars are forming, Andromeda is the real-world example that comes very close to that template. From one side of its disk to the other, a beam of light can take hundreds of thousands of years to cross. That means if a star explodes as a supernova on one side and some observer on the opposite side waits for the light, they will be waiting longer than the entire span of human history many times over. The whole system is a rotating, long-lived structure, where fast means hundreds of kilometers per second and short means tens of thousands of years. Put that next to your own galaxy and the comparison is blunt. If you could line the Milky Way up beside Andromeda like two disks on a table, your home galaxy would likely look smaller in diameter and lighter in total mass. Take everything in the Milky Way, the roughly 100,000 light-year wide disk, the central bulge, the halo of stars, the gas, the planets, the star clusters, the black holes, the supernova remnants, and the dark matter that wraps around it all. Add it up into one system. Now stack it against Andromeda. Observations suggest Andromeda's disk is larger, its stellar population is higher, and its dark matter halo is probably more massive as well. In the local group, the small cluster of galaxies your Milky Way lives in, Andromeda looks like the big sibling. So the picture you end up with is simple and slightly uncomfortable. You live in a galaxy that already feels impossibly huge, but right next door there is a bigger one with more stars and more mass, and that larger system is not drifting away with the expansion of the universe. It is moving toward you at about 110 kilometers per second, roughly 68 miles per second, closing the gap and setting up an interaction on timescales of billions of years. And that takes you straight into the next level of tension, because this isn't just a distant showpiece in the sky. Andromeda is one of the only big galaxies that's actually heading in your direction, not away. And that means the future of your entire Milky Way is tied to what this larger neighbor does next. Right now, almost every big galaxy you can see in the sky is doing the same thing. It's sliding away from you as the universe expands. You see that as redshift, their light stretched to longer, redder wavelengths because the space between you and them is growing. Andromeda is one of the rare exceptions. Its light is blue shifted. That means the wavelengths are squeezed shorter, shifted toward the blue end of the spectrum, because the distance between us and that galaxy is shrinking. Measure that shift carefully and you get a line of sight speed of about 110 kilometers per second, around 400,000 kilometers per hour, roughly 250,000 miles per hour, straight toward the Milky Way. That is the closing speed. On human scales, that is insane. At that velocity, you could go from London to New York in less than a minute. But on a distance of 2.5 million light years, 110 kilometers per second is slow motion. It means the story of Andromeda coming for you plays out over billions of years, not over human lifetimes. So for a long time, the story astronomers told about that blue shift was simple and dramatic. Given the current approach speed and the mutual gravity of the two galaxies, the expectation was in about 4 to 5 billion years, the Milky Way and Andromeda would collide head-on and merge into one larger galaxy. People even gave that future object a nickname, Milkomeda. Computer simulations showed the disk stretching, stars thrown into long tidal tails, ring-like structures rippling out, and after a few close passes, the chaotic system settling into a big, more rounded elliptical-type galaxy. In that older picture, the path was clear. Approach, direct hit, violent reshaping, new galaxy. It sounded like an appointment written into the future of the local group. The timeline matched the rough remaining lifetime of the sun's main phase, so it was easy to say, when the sun is getting old, the galaxies will be merging, and leave it at that. But then better data arrived and the story stopped being that clean. The Hubble Space Telescope and later the Gaia mission measured not only how fast Andromeda is coming toward us along our line of sight, but also how it is moving sideways across the sky. That sideways motion, the proper motion, matters a lot. A small change there can mean the difference between a direct impact and a near miss that turns into a long, complex orbital dance. With those newer measurements, the picture shifted. The current best estimates suggest that a direct center punch collision in the next 5 billion years is actually very unlikely, with odds under a couple of percent. Over the next 10 billion years, the chance of a full merger rises, perhaps to something like 50-50. Instead of a single, clean event, the future could look like a very slow, multi-pass encounter. Each pass would pull on the disks, reorder star orbits, throw out tidal streams, and rearrange gas. The details depend on the exact masses, the dark matter halos, and the current sideways velocity, all of which still have some uncertainty. The key point is, Andromeda is coming does not automatically mean one sharp impact at a fixed time. It means a complicated gravitational relationship that might take the rest of the universe's useful lifetime to fully play out. That raises the obvious worry. If two galaxies come this close, does that mean stars are going to slam into each other? Suns hitting suns like a cars in a pileup? The answer is almost certainly no. Even in a dense galactic disk, stars are incredibly small compared to the distances between them. In your region of the Milky Way, typical separations between sun-like stars are a few light years, which is tens of trillions of kilometers, or tens of trillions of miles between neighbors. If you scale the sun down to a small marble, the next marble would be several thousand kilometers away. That is how empty your part of the galaxy is. Space is not crowded for you. It is mostly nothing, with a few tiny points of matter scattered very far apart. But that empty feeling is not universal. Move into the central bulge of a big spiral galaxy and the conditions change. In those inner regions, the number of stars per unit volume shoots up. Typical separations can drop to fractions of a light year. Whole star systems operate in what is basically a downtown core, with far more neighbors, far more gravitational influences, and a much brighter sky. Instead of a mostly dark, empty night with a few pinpoints, the night would be packed with light sources. What feels like a sparse, quiet environment out where you are is just one zone in a galaxy that includes crowded stellar neighborhoods you'll never see directly. Then there are the structures orbiting around the main disks, which show you a different kind of density again. Both the Milky Way and Andromeda host globular clusters. These are roughly spherical swarms made up of up to 1 million stars each, bound tightly by their own gravity and orbiting in the outer halo of the galaxy. Andromeda has hundreds of known globular clusters. The Milky Way has over 100. Each cluster is like a compact, gravitationally locked ball of stars, many of them very old, moving as one system around the host galaxy. In a place like that, the night sky would look nothing like you're used to. Thousands of bright stars would crowd into a small fraction of the sky, with very few dark gaps between them. The concept of a dark, empty night almost disappears. The combined starlight could be so intense that your eyes would never fully adapt to darkness the way they do on Earth. You live under one star and treat that as normal. In many parts of your own galaxy and in structures around Andromeda, normal would mean a level of brightness and crowding that would feel completely alien to you. All of this star counting and spacing leads to a simple comparison that makes your situation look tiny in a new way. Energy. Your entire civilization's energy use, every power plant, every engine, every battery, is microscopic next to what just a few ordinary stars produce every second. The sun alone outputs about 380 billion megawatts continuously. That dwarfs human energy use by an absurd factor. And the sun is just one average star in a galaxy of hundreds of billions. Now scale up to Andromeda with something like 1 trillion stars. You're looking at a system that is, in effect, a trillion-engine fusion network running non-stop for billions of years. Every second, those stars are generating unimaginable amounts of energy, setting the temperature of interstellar space, driving stellar winds, powering supernova explosions and high-energy jets. Your entire history, every technological step from fire to nuclear reactors, happens on the surface of one small planet powered mostly by one star, while Andromeda casually runs 1 trillion such engines without asking your opinion. So when you say "we" in the sense of your species, you usually mean about 8 billion humans spread across one planet. It feels like a big, important number inside your own context, but it's nothing compared to the way a galaxy thinks, if you can use that word for a structure with no mind. Andromeda's "we" structurally is not a few billion organisms. It's on the order of 1 trillion stars, plus all the dark matter in its halo, plus all the gas, dust, planets, moons, comets, and asteroids bound into that system. It's a whole gravitational ecosystem with scales in light years and timescales in billions of years. You are one species, on one rock, under one star, looking across space at a machine made from 1 trillion suns and a massive dark matter backbone that you cannot see at all. You count people in billions. Andromeda counts components in trillions and more. That gap is exactly what this whole story is about. Your natural sense of scale is tuned to bodies, cities, and maybe planets. But the structures that actually set your long-term fate live many levels above that, in units where even a galaxy like the Milky Way is just one piece inside something invisible and larger. And that takes you straight into the next layer of the picture, because all these stars you can see are only the bright tracers of a much bigger, darker structure. The real bulk of both the Milky Way and Andromeda is not in the glowing disks at all. It is in huge invisible halos of dark matter that already overlap and quietly control how this whole story plays out. Right now, your whole mental picture of a galaxy is lying to you because you're focusing on the bright part and almost all the mass is in something you can't see at all. When you look at Andromeda or think about the Milky Way, you're thinking about stars, glowing gas, spiral arms, maybe a bright central bolt. That's the visible disk. But in terms of total mass, that glowing part is just a thin, shiny layer on top. Most of the mass in both galaxies is in a huge invisible structure called a dark matter halo, a three-dimensional cloud of non-luminous matter that extends far beyond the visible disk, probably out to several 100,000 light-years from the center. So if you say Andromeda is, say, 200,000 light-years across, that's just the bright disk. The dark matter halo can be much larger, spread out to distances where light from the disk is already too faint to see. Same for the Milky Way. You are sitting in a system where the stars are just the tracers, like dust caught in a much larger gravitational field built by matter that doesn't glow, doesn't reflect, and doesn't interact with light in the usual way. You might ask, how can anyone claim that all this hidden mass is there if no one has seen it directly? The answer comes from the way galaxies rotate. If only the visible matter were present, the stars and gas in the outer parts of a galaxy should orbit more slowly as you move farther out from the center, the same way planets move more slowly the farther they are from the sun. That's what basic gravity with normal matter predicts. But when astronomers measure the rotation speeds of stars and gas far from the galactic center, the speeds stay high. The outer regions move almost as fast as inner regions. Do the math with just the stars and the visible gas, and it doesn't add up. The galaxy should fly apart. The only way to make the numbers work is to add a lot of extra mass that doesn't show up in the light. Wrap the whole visible galaxy in a massive, roughly spherical dark halo. In many models, that dark matter outweighs the visible stuff by a factor of around 10. So if the stars and glowing gas are 1 unit of mass, the dark matter is 10 units. The true galaxy is not just a disk you can see, it is disk plus halo, with the halo dominating the total mass budget. Here's where things get more serious for your local situation. These halos are big enough that they don't just cover individual galaxies, they reach out toward each other. The Milky Way's halo and Andromeda's halo likely already overlap. That means gravitationally, these two galaxies are not clean, separate objects moving in empty space toward each other. They're already inside one shared dark matter structure, part of a common potential well in the local group. So when you think 2.5 million light years, that's a huge gap. You're right in one sense. That's a long distance for light to cross. But in the language of dark matter halos, the separation is not as simple. The outer parts of those halos are already in contact. You're sitting inside one side of a merged halo. Andromeda is sitting inside the other side, and the dynamics of both disks are being shaped by the same large-scale gravitational field. And this isn't just a big abstract shell out there somewhere. On small scales, right where you are, dark matter is passing through all the time. If dark matter is made of particles, and that's the leading idea, then right now a slow drizzle of those particles is streaming through your body every second. They don't interact with atoms in the way normal particles do, so you don't feel any pressure, any heat, any drag. No sense of motion, no wind. Your detectors have to be incredibly sensitive and buried deep underground just to have a chance of seeing a tiny fraction of those events. But whether you detect them or not, their gravity is already in charge. The overall shape of the Milky Way, the way its rotation curve behaves, the way stars move in the halo, the orbit of Andromeda, the odds of a future merger, all of that is set by the distribution of this invisible mass. You live in what is basically a dark matter ocean, with the bright stars floating in it like foam on the surface. So now stack all of this. You have two galaxies whose visible parts already make you feel small, and most of their true mass is in unseen halos that are already overlapping and tying them together. If even the space between is filled with a shared dark matter structure, what does your actual neighborhood look like when you zoom out one more step to the full local group of galaxies spread across tens of millions of light years? You've been treating the Milky Way and Andromeda like they're the whole story, but they're just the two biggest pieces in a much larger setup. Your actual neighborhood in the universe is something called the local group, and it's a lot bigger and a lot messier than just our galaxy plus one. The local group spans roughly 10 million light years across. That's a region where light, moving at 300,000 kilometers per second, about 186,000 miles per second, would still need around 10 million years to travel from one side to the other. Inside that volume, we know of over 30 galaxies, probably more as we keep finding ultra-faint ones. Most of them are small dwarf galaxies with far fewer stars than the Milky Way or Andromeda. The main players are three: Andromeda, the Milky Way, and a smaller spiral called the Triangulum Galaxy. Those three carry most of the stellar mass. Everything else is basically small satellites and debris. So instead of one big galaxy floating alone, you live in a small gravitationally bound collection of galaxies. That changes the way you should think about here. But even that isn't just a random cloud of objects in all directions. The structure has a shape. Roughly speaking, the local group looks like a dumbbell. On one side, you have the Milky Way and its group of satellite galaxies. On the other side, you have Andromeda with its own swarm of satellites. In between, about 2.5 million light years apart, is the main gap. The overall center of mass, the balance point of the whole thing, sits somewhere between the two big spirals, but slightly closer to Andromeda because it's likely more massive. So when you say our galaxy is moving toward Andromeda, what's really happening is both big galaxies are moving within a shared gravitational field toward their common center of mass, dragging their satellite systems along. You can think of it this way, not as two isolated giants closing in, but as a double system, already linked with each side carrying a cloud of smaller galaxies. Which leads to the next question. What exactly are those smaller galaxies doing, and why are there so many of them? Around both the Milky Way and Andromeda are dozens of dwarf galaxies, the large and small Magellanic Clouds near us, various dwarf spherical galaxies around Andromeda, and many more. These are systems with far fewer stars, often only millions or tens of millions instead of billions or trillions. They orbit the larger galaxies like crumbs around a pair of loaves. But these crumbs aren't just peacefully circling forever. Many of them are being stretched and torn apart by tidal forces. As a dwarf galaxy orbits close to a massive host, the near side and far side of its gravitational pull is slightly different. Over time, that difference can pull stars out, forming long, faint streams that wrap around the host. Observers show these tidal streams around both the Milky Way and Andromeda. This is not a rare special effect. This is the normal way big galaxies grow. They eat smaller ones. So your local group is not a polite set of separate objects minding their own business. It's a system where the larger members slowly strip and absorb the smaller ones. That naturally raises a harder question. If big galaxies are eating dwarfs now, what does that say about their past? Both the Milky Way and Andromeda carry scars that point to multiple past mergers. Your galaxy's disk is slightly warped. There are known stellar streams, like the Sagittarius stream wrapping around the Milky Way, made of stars that used to belong to smaller galaxies now being digested. The outer halo is lumpy and uneven, not the smooth, clean structure you'd expect if nothing had disturbed it. Andromeda shows even clearer evidence: pronounced streams, shells, and asymmetries in its halo, strong signs that it has torn apart and absorbed several smaller galaxies over time. The local group, in other words, is not static. It's an ongoing, slow-motion demolition derby played out over millions to billions of years and across millions of light years. Dwarfs fall in, get stripped, and eventually their stars blend into the... Both the Milky Way and Andromeda carry scars that point to multiple past mergers. Your galaxy's disk is slightly warped. There are known stellar streams, like the Sagittarius stream wrapping around the Milky Way, made of stars that used to belong to smaller galaxies now being digested. The outer halo is lumpy and uneven, not the smooth, clean structure you'd expect if nothing had disturbed it. Andromeda shows even clearer evidence: pronounced streams, shells, and asymmetries in its halo, strong signs that it has torn apart and absorbed several smaller galaxies over time. The local group, in other words, is not static. It's an ongoing, slow-motion demolition derby played out over millions to billions of years and across millions of light years. Dwarfs fall in, get stripped, and eventually their stars blend into the halos and disks of the big spirals. Triangulum may also be interacting with Andromeda in complex ways. On human timescales, everything looks frozen. On cosmic timescales, this region is constantly rearranging itself. That knocks out another common wrong idea: the idea that galaxies are isolated islands in space, just drifting in a quiet void. When you zoom out to the local group scale, a single big galaxy like Andromeda stops looking like the universe and turns into just one node in a small gravitational family. The Milky Way is one node. Andromeda is another bigger one. Triangulum is a smaller node. The dwarfs are like secondary branches hanging off the main ones. And that whole family sits inside the larger dark matter structure we talked about earlier. The local group is bound together by gravity, moving as one system through space, while smaller pieces inside it merge, get stripped, or fall into larger members. On the 10 million light-year scale, Andromeda is not the entire story. It's just one lobe of a small cluster. And here's where the tension jumps again, because as big as this all feels, the local group itself is tiny compared to the structures above it. 10 million light-years sounds enormous, and it is, but on the scale of the cosmic web, it's just one dot in a filament among many. Once you step out to the level of superclusters and the full cosmic web, even Andromeda, even your entire local group, gets reduced to a small feature in a much larger pattern. So you've gone from planet to solar system, to galaxy, to two-galaxy interaction, to a small cluster of galaxies. And every time, what felt huge at one level turns into a minor detail at the next. The local group is not the end of that ladder. It's just one more rung, and the next rung up is where even clusters of galaxies start to shrink into tiny marks on maps that span hundreds of millions of light years. You've seen that the local group is already a whole mini environment, but even that is just a small patch of something bigger. Your local group is part of a structure called the Virgo supercluster, a collection of galaxy groups and clusters spread over tens of millions of light years. And that Virgo supercluster is itself part of an even larger region called the Laniakea supercluster, which stretches across roughly 500 million light years. On that scale, 500 million light years across, the Milky Way and Andromeda are not big structures anymore. They're single pixels in a huge gravitational flow pattern. When astronomers map galaxy motions in this region, they see that thousands of galaxies, including ours, are drifting along toward large mass concentrations like the Virgo cluster and beyond. You and Andromeda are just small components embedded in this larger river of matter, all sliding around under the pull of gravity on scales your usual language can barely describe. So, what does this river actually look like when you draw it out? It doesn't look like a random spray of dots. It looks like a web. On the largest scales we can map, galaxies and clusters are not evenly spread. They line up along vast filaments, huge threads and walls that can run for tens to hundreds of millions of light years. Between those filaments sit enormous voids, regions where there are very few galaxies at all, just thin gas and dark matter. This whole design is called the cosmic web. It's what you get when gravity pulls on tiny early density fluctuations for billions of years in an expanding universe. Recent work has gone even further and found signs that some of these filaments themselves rotate as single structures, tens to hundreds of millions of light years long, with galaxies moving around their axes. So not only do individual galaxies spin and clusters move, but whole multi-tens of millions of light years long strands of matter can show coherent rotation. You're dealing with motions and patterns that make even a galaxy-galaxy collision feel like a minor detail happening inside a much bigger frame. Now drop Andromeda into that picture and see what happens to your sense of scale. On a map of a supercluster or of Laniakea as a whole, big spirals like the Milky Way and Andromeda are just dots or tiny symbols. Their internal sizes, 100 to maybe 200,000 light years across, vanish when you zoom out to hundreds of millions of light years. The ratio is brutal. A galaxy that looked enormous when you first met it now acts like a punctuation mark on a gigantic grid. Your entire local group, that 10 million light-year region with all its internal drama, gets reduced to a tiny marker on a large-scale flow map. At that level, no one cares which spiral has more stars. The important thing is which way the whole clump is moving in the broader pattern. And the movement on these scales is not simple away or toward. Here, gravity and cosmic expansion are fighting it out. On small enough scales, like inside the local group, gravity wins, so your galaxies stay bound together. On very large scales, expansion wins, so distant clusters recede from each other and from you. In between, on cluster and supercluster scales, you get a mix. Groups like yours fall toward bigger clusters. Filaments feed those clusters with fresh galaxies, and everything is superimposed on the overall stretching of space. So Andromeda is not just coming at us in a straight, isolated line. The Milky Way and Andromeda are both moving through a complex gravitational landscape carved by dark matter and ordinary matter, while the entire fabric of the universe continues to expand. Their mutual approach is happening on top of a larger drift, like two boats slowly steering toward each other while both are also caught in a broad ocean current. Here's the psychological hit in all this. Every time you decide, okay, this size is enough, this is big enough to feel like the universe, cosmology calmly adds another layer above it. Earth felt big until you learned about the solar system. The solar system felt big until you looked at the Milky Way. The Milky Way felt big until you met Andromeda. Andromeda felt big until you saw the local group. The local group felt big until you saw Virgo and Laniakea and the full cosmic web. By the time you're thinking about 500 million light-year structures and 100 million light-year filaments, a single giant spiral galaxy with its trillion stars becomes just a dot in a pattern that doesn't care whether your species ever figured any of this out. The web will keep evolving. Filaments will keep feeding clusters. Superclusters will keep stretching and flowing, no matter what happens on one small planet and one small arm of one small galaxy. And yet, you're not done zooming out. You still haven't compared your tiny slice of the universe to the entire observable universe, or put your own timeline next to the timescales these structures live on. When you do that, even superclusters stop looking like the final step, and Andromeda's power over your fate starts to look like a small part of a much longer, much slower story. The size differences are already harsh, but the time differences are worse. Your whole story as a species runs on fast forward compared to the clocks the universe is using. Modern humans, Homo sapiens, have been around maybe 300,000 years. That sounds ancient when you're talking about history books or archaeology, but light from Andromeda takes about 2.5 million years to get here. So the photons hitting your eyes tonight from that faint smudge in the sky left Andromeda more than 2 million years before anything recognizably you existed to see them. When those photons started their trip, there were no cities, no writing, no agriculture, no humans. Your entire species fits into a time window that is shorter than the travel time of one beam of light crossing the Andromeda Milky Way gap. You think of yourself as a modern observer, but from the light's point of view, you only showed up at the last instant of a very long journey. So, if your species' history is that short, what does your timeline look like when you compare it to the way your own galaxy moves? Take one orbit of the Sun around the center of the Milky Way. That galactic year is about 230 million Earth years. The dinosaurs went extinct about 66 million years ago, so that mass extinction was less than one full galactic year ago. Dinosaurs lived, thrived, and disappeared during the last quarter of the current orbit. Humanity, all of Homo sapiens, lives in a tiny sliver of that same orbit, around 0.0013 of a single galactic year. That's just a little more than 1,000th of one lap. Everything you call history sits inside a slice so small that if you tried to mark it on a circle representing one full orbit, it would look like a line that's basically too thin to draw. The galaxy has been going around the center over and over for billions of years. You and every story you've ever heard exist in a barely noticeable fraction of one turn. Now, push this further, because the galaxy itself is not frozen in time either. If the Milky Way and Andromeda eventually merge, that process is not a quick event. It could take billions of years from first serious interaction to final settled remnant. A sun-like star lived for roughly 10 billion years. That means a star can be born, go through its stable phase, run through its fuel, and die, all during one long, slow reshaping of its host galaxy as it merges with another one. While a merger is unfolding, the orbits of stars are changing. Disks are warping, halos are mixing, and whole streams of stars are being thrown into new trajectories. But each individual star is running its life cycle on its own clock. A star's whole life can fit completely inside just one phase of a galaxy-galaxy interaction. Your galaxy structure is slow enough that entire stellar generations rise and fall while it's still in the middle of one big gravitational project. That makes the next contrast even more brutal because you've been focusing on the Andromeda Milky Way future like it's the main thing to worry about. And for Earth, it simply isn't. Long before any definite merger, the Sun itself changes in ways that matter to you. Over the next billion years or so, the Sun will slowly brighten. That increase in luminosity will push Earth's climate toward a point where complex life as you know it becomes impossible. Oceans will gradually evaporate, the surface will heat up, and your planet will move out of the comfortable zone for liquid water. By around 5 billion years from now, the Sun will have left its stable main phase and will swell into a red giant. Its outer layers will expand and the inner planets will be scorched or engulfed. Earth as a habitable world will be long gone by the time any late-stage Milky Way-Andromeda merger details really finish playing out. The galaxy-scale events you're stressing over happen on timescales where the specific planet you care about is already finished as a place for life like you. So put all of that together. Your species, a few 100,000 years. Your recorded civilization, maybe a few thousand years. Your galaxy's orbit, hundreds of millions of years per lap. Galaxy mergers, billions of years. Star lifetimes, up to tens of billions of years. In that stack, your whole civilization is not a chapter in the galaxy's life. It's more like a brief electrical glitch, a tiny, fast fluctuation in one small region of one orbit, barely noticeable against the background of hundreds of millions of years of normal galactic behavior. Andromeda doesn't just dwarf you in size, it dwarfs you in time. The structures you're looking at in the sky have been around for billions of years before you and will continue for billions after, changing slowly, reshaping gradually, while your entire species arc comes and goes in a thin slice that hardly registers on their timeline. If your entire history is that short compared to a galaxy's life, the next question is, what about the things at the very center of these systems? The objects so massive and so compact that they can outlast disks and mergers and orbits. The supermassive black holes that will still be there long after your planet is gone. Right now, everything we've talked about still feels spread out. Stars, disks, halos, orbits. But at the very center of both the Milky Way and Andromeda, the story flips. All that mass and time gets focused into tiny regions with absurd density, the supermassive black holes that act like central engines for their galaxies. Your own galaxy's central black hole is called Sagittarius A star. It has a mass of about 4 million suns. Not 4 suns, not 4,000, 4 million times the mass of the sun, all compressed into a region smaller than your solar system. Andromeda's central black hole is even extremer. Current estimates put it in the tens of millions of solar masses range. So while you orbit one star with one solar mass, the centers of these galaxies are anchored by objects with millions to tens of millions of solar masses. These black holes are not vacuum cleaners sucking everything in from across the galaxy. They mostly just sit there and dominate the gravity in their inner few light years. But when gas and stars fall too close, they can light up as active galactic nuclei, blasting out energy across huge distances. So here's the obvious follow-up. If the galaxies themselves might merge one day, what happens to the monsters at their centers? If and when the Milky Way and Andromeda finally fuse into one galaxy, their central black holes won't just ignore each other. As the galactic cores sink together, each black hole drags a crowd of stars and gas with it. Through a process called dynamical friction, the black holes gradually lose orbital energy to the surrounding stars, and their separations shrink. Over time, they settle into a bound pair orbiting each other at close range in the merged galaxy's core. As they get closer, they start to radiate energy in the form of gravitational waves, ripples in space-time itself. Those waves carry away energy and angular momentum, tightening the orbit even further. Eventually, the two black holes merge into a single, even more massive black hole. The final moments of that merger release a burst of gravitational waves so strong that a detector like LISA, the planned space-based observatory, could pick it up from millions or even billions of light years away. But from your point of view, as a human observer, what would that actually look like? Would you see some kind of bright explosion in the sky? Even if humans somehow lasted long enough to be around when this happens, you would not see a black hole merger with your naked eyes like you see a supernova. The visible light from the final coalescence might not be very impressive. The real action is in gravitational waves and in high-energy radiation like X-rays and gamma rays, coming from hot gas near the end horizons. Those signals need specialized instruments to detect. To your eyes, the galaxy's center might just look like a bright, compact region as usual. Meanwhile, space-time itself would be ringing, like a massive bell being struck. But the distortion at Earth's location would be incredibly tiny, far smaller than the width of a proton. Only very sensitive detectors could notice. Everyday life wouldn't suddenly flip over when the central black holes merge. The drama is on the level of the geometry of the universe, not on the level of buildings falling over. The scale of the event is still hard to overstate. You're talking about an object with possibly tens of millions times the mass of the sun collapsing into a single, more massive black hole. The region around it where not even light can escape, the event horizon, would be larger than your entire solar system. If you replace the sun with such a black hole, its event horizon could extend beyond the orbit of Earth and out toward or past the outer planets, depending on the exact mass. And yet, when you zoom back out to galaxy scales, that enormous deadly sphere is still just a microscopic dot at the center of a system hundreds of thousands of light years across. Zoom out again to the level of the local group or the supercluster, and that huge central black hole becomes basically a coordinate on a chart, a point with a mass label on a diagram of a much larger structure. Its direct influence doesn't reach those scales. It is both unimaginably powerful and completely trivial depending on how far out you're looking. And that brings you back once again to your own place in this story. In a future merged galaxy, call it Milkomeda or whatever name sticks, there will likely be a central black hole that includes the mass of both current cores. That object will have swallowed stars and gas and smaller black holes over billions of years. The total energy released in gravitational waves and radiation during that process will be beyond what you can generate as a civilization. Against that energy budget, your entire planetary history is a rounding error. Every rocket launch, every power plant, every signal ever sent, all of it added together is negligible compared to what a single black hole merger does to spacetime in a few seconds to minutes. You live on a small rock under one star in the outskirts of one galaxy, looking toward a future where even the cores of galaxies merge and move on. The central engine of that future system will carry the mass of millions of suns, and your own existence won't show up in any of the equations that describe it. If even the heart of a merged galaxy treats you as noise, why does Andromeda still matter so much to your understanding of the universe? Because it isn't just a threat or a future collision partner, it's also one of the best labs you have for watching how galaxies like yours are built, changed, and destroyed over cosmic time. You keep treating Andromeda like a threat, but for astronomers, it's also something else. It's a tool. Because it's both huge and relatively close, Andromeda is one of the best laboratories you have for studying what big spiral galaxies really are and how they change over time. It's close enough that powerful telescopes don't just see it as a smooth glow. They can actually pick out individual stars in many regions. The Hubble Space Telescope has resolved hundreds of millions of Andromeda stars one by one in detailed surveys. Instead of a blurry smear, you get sharp points, each point a star with a color, a brightness, a place in the galaxy. So what do you do with that much detail? What does all that star-by-star information actually buy you? Across Andromeda's disk, you don't just see random stars sprinkled everywhere. You see patterns. Stars come in different colors and brightnesses, which reflect their ages and compositions. Blue, bright stars tend to be young and massive, burning through their fuel quickly. Redder, dimmer stars tend to be older and lower mass. By measuring those properties in different parts of Andromeda, astronomers can reconstruct where star formation has been strong, where it has faded, and when different regions lit up. You can see rings where star formation surged after a pass encounter. You can see zones where older, metal-poor stars dominate, telling you these regions formed early, when the universe had fewer heavy elements. You can see pockets where metal-rich stars cluster, showing where gas enriched by previous generations of stars was recycled into new ones. In other words, Andromeda's disk is not just a snapshot, it's a record of billions of years of activity, written in starlight. The key point is that these patterns tell you how a galaxy like yours builds itself, but with a view you can't get at home. The Milky Way is hard to study from the inside. You're sitting in the disk, behind clouds of dust, with only a partial view in any direction. It's like trying to draw a city map while standing in one apartment, looking out one window at a time. You see streets, a few buildings, some landmarks, but not the overall shape. Andromeda solves that problem. You see it from the outside. You can trace its spiral arms, its bar, its bulge, its halo, all from a single vantage point. You can point different instruments at different parts and build a full, coherent model of the whole system. Every bit of structure you decode in Andromeda feeds back into your understanding of the Milky Way. If Andromeda's disk shows certain patterns between its arms and star ages, you ask whether your galaxy's arms behave the same way. If Andromeda's halo shows a certain mix of star types, you check for the same mix in your own halo. It becomes a comparison sample, a reference case. But Andromeda isn't some clean, untouched spiral. When you look more carefully, especially in its outer regions, you find scars. Faint, stretched out streams of stars wrap around it. Asymmetric features stick out from its halo. These are tidal remnants, the leftovers of smaller galaxies that got too close and were ripped apart by Andromeda's gravity. Their stars have been smeared into long arcs and shells, still orbiting as a group but no longer bound into a neat separate system. Your own Milky Way shows similar signs, like the Sagittarius stream and other faint structures in the halo. Put both galaxies side by side, and you see the same story repeated. Big spirals eating dwarfs over and over, slowly building up their mass by cannibalizing smaller systems. The outer halos are full of these fossil features, like frozen waves left over from old collisions. Andromeda just makes that story easier to read because you can see it all in one frame. So you end up with a strange relationship. The galaxy that makes you feel tiny and fragile when you think about its size and its future collision path is also the one that gives you a clear timeline of how galaxies like yours are born, grow, and change. You're using a trillion-star machine as a textbook. You look at the distribution of its stars, its gas, its streams, its black hole, and you write down rules about disk formation, halo buildup, merger scars, and star formation cycles. Then you apply those rules back to your own galaxy, which you can't see from the outside. That's the twist here. Andromeda doesn't care about you. It doesn't know you exist. It is just following gravity and physics on billion-year timescales. But you are using it as a time machine and a mirror. When you stare at Andromeda, you're looking into another massive spiral at a specific point in its evolution. You see what long-term merging does to a galaxy. You see how star formation moves around the disk. You see how a halo fills with streams. From that, you infer what has already happened to the Milky Way and what is likely still coming. So a galaxy that completely outclasses you in mass and scale and may eventually merge with your own galaxy also gives you the data you need to understand just how small and temporary your position really is. It turns your feeling of insignificance into a measurable, testable thing. You can say, this is how galaxies evolve. This is where we are in that process. This is roughly what will happen next, because a giant neighbor lets you read its history. And there's one more layer to this, because Andromeda is not just a good lab for structure and evolution. It's also special in another way. It's one of the only massive galaxies that is not running away from you with the expansion of the universe. It's moving toward you while almost everything else is receding. That makes your little patch of the cosmos a weird exception, and it sets up a very different kind of special for your position in space and time. Everywhere else, galaxies are running away from you. So why is this one coming closer? On large scales, the universe is doing something very simple. Space itself is expanding. That expansion stretches the light from distant galaxies, shifting it to longer, redder wavelengths. That pattern is called the Hubble flow, and it means that on average, the farther away a galaxy is, the faster it appears to recede. When you look out with big telescopes, almost every major galaxy shows that redshift signature. Andromeda does not. Its light is blue shifted. The wavelengths are squeezed instead of stretched. That's your direct evidence that on the scale of the local group, local gravity is beating the general expansion. Gravity from the Milky Way, Andromeda, the dark matter halos, and the rest of the local group's mass is strong enough that this small patch has decoupled from the Hubble flow. The universe can stretch all it wants on very large scales, but in this particular patch, gravity has enough leverage to override it locally. Now, push this forward in time and the picture gets more extreme. Look beyond the local group and remember that the expansion of the universe is not slowing down overall. It's accelerating because of dark energy. Over very long timescales, that acceleration will carry most other galaxies and clusters beyond your observable horizon. Their light will never reach you, no matter how long you wait. They don't stop existing, but they stop being visible to any observer bound to your local group. Fast forward far enough, and a future astronomer sitting inside the Milky-Way-type galaxy would look out and see no external galaxies at all, just their own system floating in what appears to be an empty universe. The cosmic microwave background would fade. The large-scale structure would be invisible. The universe would still be full of other structures beyond the horizon, but all direct evidence of them would be gone. That sets up a very specific irony. The galaxy that feels threatening to you right now, because it's big and on an inbound path, is also the one that reason future intelligences in this region might have any external galaxy to study at all. Without Andromeda, the local group would be much smaller and less massive. Once everything outside got dragged beyond the horizon, an observer here might only see one relatively modest galaxy. With Andromeda, you get a larger, brighter merged system, and crucially, you get another giant spiral to study now before the universe hides everything else from view. In other words, the same gravitational setup that is slowly bringing Andromeda toward you is also what makes your corner of the universe scientifically rich at this particular moment. It gives you an approaching galaxy to measure, a dynamical problem to solve, and a second major spiral to compare against your own. The threat and the opportunity are the same physical situation, just viewed from different angles. And that leads to the last point in this section, because your current vantage point is not guaranteed everywhere or every when. You happen to live in a time and place where you can see another giant spiral galaxy clearly, measure its distance and speed, track its motion across the sky, and use all of that to predict multiple possible futures for the whole local group. You have access to both the local gravitational story and the large-scale cosmological story at once. In many other regions of the universe, or in much later eras, that won't be true. Observers might see only their own galaxy and think the universe is static and empty. The clues you use today to understand expansion, dark matter, and structure formation simply won't be visible to them. Right now, from this small planet, you can still connect the dots between local gravity and global expansion, between Andromeda coming closer and almost everything else running away. So you're in a weirdly special patch, not because the universe cares about you, but because the timing and the local conditions just happen to line up. You're alive in the brief window when another giant galaxy is both visible and inbound, and when the wider cosmic web is still on display. But even that window sits inside something bigger again, because beyond the local group, beyond Laniakea, there's the full observable universe, and on that scale, even two colliding giant spirals are just dust. You've been stretching your sense of distance step by step, but there's still one more level where everything you care about turns into dust on a map. The observable universe has a radius of about 46 billion light years, not 13.8 billion, even though that's the age of the universe, but roughly 46 billion. The reason is simple and brutal. While light has been traveling toward you for 13.8 billion years, space itself has been expanding underneath it, so the galaxies that sent that light are now much farther away than distance equals speed times time would suggest. Put your local group next to that. The local group is about 10 million light years across. Compare 10 million to 46 billion. Your entire cluster of galaxies is microscopic on that scale. If the observable universe were shrunk to the size of Earth, the local group would be smaller than a grain of sand on that Earth. And inside that grain, the Milky Way and Andromeda are just two bright spots. So the natural question is, how many galaxies are you actually talking about when you say the universe? Current estimates say there are at least hundreds of billions of galaxies in the observable universe, and some studies push that number up toward a couple of trillion. Not stars, galaxies, each one containing hundreds of billions to perhaps a trillion stars each, the way the Milky Way and Andromeda do. When you multiply those, you get a total star count so large that saying the number out loud doesn't help you at all. It just turns into a string of zeros. In that context, Andromeda stops being the big one. It becomes one entry in an enormous catalog. If you tried to scroll through a list of all the galaxies in the observable universe with one line per galaxy, you couldn't even hold the idea of the index in your head. Your big, dangerous neighbor, the thing that can completely reshape the Milky Way one day, is statistically just another data point. Behind all of this structure, there's one more layer that defines the true edge of what you can see. That's the cosmic microwave background, the leftover light from when the universe was about 380,000 years old. Before that time, the universe was hot and dense enough that light couldn't travel freely. It kept bouncing off charged particles. When things cooled enough, matter and radiation decoupled, and photons could finally stream through space without constantly scattering. Some of that light has been traveling ever since, stretched by expansion into microwave wavelength. When you detect the cosmic microwave background, you're seeing as far back in time as normal light lets you see. Beyond that surface, the universe still exists, but no light from those earlier moments has reached you yet. It's not that there's a wall, it's that the signals haven't had enough time. Andromeda, the Milky Way, every galaxy cluster and filament you've heard about all sit in front of that ancient glow. In the full picture, they are just foreground features against the background that marks the very young universe. Even Andromeda is just a small speck on that backdrop. So at this point, it helps to recap the hierarchy in plain terms with the rough size scales. You start at you, a human measuring maybe a couple of meters in height. Step up to Earth, around 10,000 kilometers across. Step up to the solar system, where typical distances are in tens of billions of kilometers, which is around 10 trillion meters, or 10 to the power of 13 meters. Step up again to the Milky Way, about 100,000 light years. Go out to the local group, about 10 million light years. Then you hit supercluster scales, tens to hundreds of millions of light years. Finally, you hit the observable universe with a radius of about 10 billion light years, or more precisely around 46 billion. Andromeda sits only one step above your own galaxy in this ladder. It's not at the top, it's just the next rung, the next level where your intuition fails. There are multiple levels above it, and at each one, what looked huge at the previous level shrinks to a tiny feature. So here's the final scale gut punch for this part of the story. Yes, Andromeda dwarfs you. It dwarfs your planet, your species, your entire sense of home galaxy. Its mass, size, and timescales make everything human look like noise. But the universe doesn't treat Andromeda as anything special. To the large-scale structure, it's one more small lump in a sea of lumps. To the observable universe, it's one tiny structure flickering for a few billion years in a 13.8 billion-year-old expanding space-time. In other words, you and Andromeda are on the same side of the real divide. Both of you are tiny. One is tiny in human units, the other is tiny in cosmological units. You're on a small world around one star. Andromeda is a slightly bigger than average bright patch in a sky full of bright patches, many of which you will never even resolve individually. The universe doesn't separate you and Andromeda into insignificant and important. It classifies both as minor structures and moves on. So if you are that small in space and that brief in time, what does your size actually mean? Does it make you irrelevant, or does it change what your brief local existence can be used for, now that you know just how far down the ladder you really are? Here's the part that stings. You're not the main character here. On Andromeda scale, you're less than background noise. That galaxy does not care whether you exist, whether humans ever stood on this planet, or whether anyone ever pointed a telescope at it. Nothing about its structure, its spiral arms, its dark matter halo, or its future merger odds depend on you. From Andromeda's point of view, you're statistical noise sitting on one random planet in one unremarkable arm of a neighboring spiral that it will eventually distort, merge with, or just ignore as gravity dictates. If you vanished tomorrow, none of the equations that describe Andromeda would need to change. But here's the weird flip. Even though you are dynamically irrelevant, your point of view is rare. You're one of the very few arrangements of atoms we know about that can even ask, how big is Andromeda? How far away is it? What's going to happen to it? You're a self-aware measurement device, built out of hydrogen and helium that were forged into heavier elements inside stars, then mixed into gas clouds, then turned into a planet, then turned into living cells, then turned into a nervous system that can do physics. You are the universe doing experiments on itself. You're not special because gravity listens to you. It doesn't. You're special because you're one of the tiny corners where the universe has become able to look back and say, okay, what is this thing exactly? Your brain is just chemistry, but that chemistry is now running models of galaxies, dark matter, and cosmic expansion, and those models actually match the data. That leads to a different kind of unsettling idea. The universe is completely indifferent to you, but at the same time, it is weirdly legible to you. Space doesn't care if you're comfortable, but it still follows rules you can write down. With a few telescopes on a mountain, a space observatory or two, some spectrometers, and the math of relativity, you can measure Andromeda's speed toward you to a precision of a few kilometers per second, a few miles per second. You can estimate its distance in parsecs and light years. You can put error bars on its mass. You can simulate possible future orbits of the Milky Way Andromeda system on a computer. So you have this combination: total cosmic indifference plus high intelligibility. You are entirely irrelevant to Andromeda's evolution, but you can still write down a model that predicts its path to within a fraction of a degree over millions of years. You're too small to matter to the galaxy, but not too small to understand it. That's the real horror here. Not that you're insignificant, but that you can quantify your own insignificance in ridiculous detail. That's where your only real leverage sits. You can't move galaxies, you can't push on dark matter halos, you can't change the rate of cosmic expansion. You're not going to steer Andromeda away from the Milky Way by any technology you can realistically imagine. But you can move something smaller and closer. You can move your species' understanding. You can decide to build better instruments, bigger mirrors, more sensitive detectors. You can decide that reading the faint light from Andromeda's oldest stars is worth decades of work. You can map where its dark matter halo must be by tracing the motions of stars and gas. You can measure its proper motion, that tiny sideways drift across the sky, in micro arcseconds per year. You can reconstruct its merger history from the stellar streams in its halo, and then compare that to the scars in your own galaxy. You can tune your models until Andromeda and the Milky Way both fit into the same physical story, one that explains how galaxies grow, collide, and fade over billions of years. On the ground, that looks like very ordinary human activity: building observatories, launching satellites, writing software, analyzing noisy data at 2 a.m. But in terms of what the universe is doing, it's a small part of itself turning inward and decoding patterns in the larger part. Your brief existence becomes about decoding things vastly bigger than you, not about outmuscling them. You don't change Andromeda, you change how clearly your species can see Andromeda. So when you hear a line like, Andromeda is 2.5 million light-years away and up to 260,000 light-years across, don't let it slide by as just a big number you're supposed to be impressed by. Hear what it actually implies. You are a tiny, local pocket of matter, a few dozen kilometers of atmosphere deep, on a rock about 12,742 kilometers wide, roughly 7,900 miles, orbiting one average star. And from that position, you have worked out distances of millions of light years and sizes of hundreds of thousands of light years, with units precise enough to plan spacecraft trajectories and test general relativity. That doesn't make you larger. Andromeda is still massive. Your galaxy is still just one piece in a web. The observable universe is still far beyond both. But it changes what your smallness means. It stops being just, you are tiny and that's the end of it, and becomes, you are tiny and you are aware of it, and you can map it, and you can teach it before your brief window closes. You don't control the story of the universe. You don't even control the story of your own galaxy. But you do control what you do with the few tens of years you get inside one small civilization, on one world, in one arm of one spiral falling slowly toward a bigger one. You can ignore all of this and stay inside local problems, or you can keep pushing the scale. Keep forcing your brain to stretch from meters and kilometers out to light years and billions of light years, and let that recalibrate what big and important actually mean for a creature like you. So the final line is simple. Andromeda doesn't notice you, and it never will, but you've noticed Andromeda. You've measured it, named it, modeled it, and you're using it to understand where your galaxy came from and where it's going. You are a very small part of the universe that has realized how small it is and decided to look up anyway. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.